Hey everyone, today's test day. I don't know when I did it yesterday, but evidently I had mentioned that the test was going to be Friday. I'm not sure how that came to be. Anyway, the test is definitely today. It'll open up during your class time. I have, I think, 3 students who've indicated to me that they cannot make it due to work responsibilities or they're living overseas and it wouldn't be convenient. So if you're in one of those situations, I can either start it early or postpone it. Um, Yesterday's review session, I think we covered every single question. I was hoping to take the time last night and sort of index that section, but I was unable to do so. I was still putting finishing touches on the exam. Working on that a little bit more this morning. The issues mostly were how to get answers in the boxes correctly with the correct units. So I experimented with a bunch without having to answer some prompt about, do you know that your number's not supposed to have units or something like that. So I've been practicing with the exam. I think I have it in pretty good shape. It turns out it's 19 questions long. The multiple choice were 5 points apiece, and the either fill in the blank or do the calculations, those were 6 points apiece. I took it this morning. It took me 12 minutes to complete it from the beginning to the end. So I think that's just about the right amount of time, but I will allow you an hour and a half to work on this one, even though I think that'll be a little bit of an overkill. Most of you, I would imagine, since so many of it are so much it's multiple choice, that you'll be done with it a lot sooner. On the long answer questions, for example, I had a ticketing problem, and that has 2 parts. Same thing with the fencing problem, same thing with the inventory problem, same thing with the box with the open top. All of those have 2 parts. So you'll read through the one question, the last one thing, and then you read through the second one. The setup will be exactly the same. I copied and pasted. I've checked my language skills on each of the tests questions many times over, and I think I have them as close to right as I possibly can. It turns out that I'll have a few questions in here that the answers won't show up right away, or your grade won't show up right away because I'll have to hand grade a few of those. That's fine, but for the most part, you'll be able to tell the ones that you got right on the multiple choice, and several of the short answers you'll be able to tell right away. Once everyone's taken the test, then I'll enable the process for you to go back and look to see exactly what you did on the test and exactly what the right answers were. We'll be there summarizing the results on the exam. I'm not going to have you summarize the result all the way through on a problem, but I might ask maybe on a ticketing question, I might ask how many tickets will they sell during the maximum to get the maximum revenue, or what's the price per ticket, or what's the length of the short side of the fence, or what's the number of boxes of flour that you should order at a time. But I'm not going to have you list like all of the things down there on any one problem. But in order for you to get the the right thing I'm looking for, if you can understand all those bits, that's certainly going to be beneficial. Could you go over 3H and 3I? Sure, Jessica. Those are really good questions, and these are things that I'm not sure why it gets so confusing for students, but it does. What do you know about the value of the first derivative at the point we label W? I'll do my best to recreate the graph. Let's see, a dot, a star in each critical point, star, 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 a dot on each inflection point. That's where the graph goes straight. Looks like right about there. Maybe right about there. Probably right about there. I'm supposed to label those critical points starting with W, and just enough letters for that, I guess. W, X, Y. I only had one more. A dot on each inflection point. Label these A, B, C. Okay, so letter H. What do we know about the value of the first derivative at the point we labeled W? All right, yeah, right there, the value of that first derivative right there at W is definitely 0. The first derivative tells us what the slope of the graph is at every point, and right at W, that's the classic slope of 0, so that is correct. So the value of the first derivative at W is 0. What do we know about the value of the first derivative at the point we labeled A? There's the point we labeled A. The value of the first derivative there must be a positive number. So that must be, so the answer to that is it is bigger than 0 or it is positive. So I could have just as easily asked, and maybe this would, maybe I should have included a few more on this one. Let's H, I, J. Let's consider this J. What do we know about the value of the second derivative at the point marked how about X? So tell me everything you know about the second derivative at that point marked X. What all-encompassing statement can you make? And then back that up with why that statement is, what the statement that you made, why that statement is true. So think a little bit there. What do we know about the value of the second derivative at the point marked X? Okay, Matthew, yeah, I'll go back and get G in just a second. So what do we know? There's our point marked X. What do we know about the value of the second derivative? And why do we know that? Negative, since it's concave down, exactly right. Okay, what do we know about the value of the second derivative at marked X? Yep, it's a negative number, concave down, exactly right. Okay, how about what do we know about the value of the second derivative at the point marked with a B? So same question, Hij. I guess this might be part K. Let's just ensure that you folks know exactly what each of those derivatives show and what those mean. There we are, the point marked B, also known as an inflection point. Now, the value of the second derivative here is not 0. Remember, the second derivative tells us about concavity. Okay, and what do we know about the concavity right there at B? What do we know about the concavity, I guess, at any inflection point? It's 0, no concavity, exactly. No concavity at that point. So I didn't ask, Drew, I didn't ask what the concavity was. I asked the value of the second derivative. Your reasoning was perfectly right on. There's no concavity. Okay, so if I go back through and list these points, at point W, the first derivative is 0, the second derivative is positive. At point A, the first derivative is positive, the second derivative is 0. At the point marked X, as we just said, the first derivative is 0, the second derivative is negative. At point B, the first derivative is negative since it's decreasing, the function is decreasing, the second derivative is 0. At point Y, the first derivative is 0, the second derivative is positive because the graph is concave up and we have a slope of 0. At point C, the first derivative is positive because the function is increasing. The second derivative is 0 because the graph has no concavity at that point. So we're going to move back. Yeah, there's no concavity for the inflection points. Exactly right. There's no concavity at any inflection points. That's how we define them after all. So I wanted to march back. I think someone asked me something about letter G. What's the concavity on the graph for October 1st, 2010? So this is the value of the business T months after January 1st. So it would be February would be 1, March, April, May, June, July, August, September, October. That would be on the 10th month. So the 10th month is right about in here. The concavity of the graph right there would be concave down. Those are really excellent questions. I think most of the multiple choice, a lot of the multiple choice deals with situations like this. So how about if I pose this question to you? Tell me an interval Find me an interval on here where the slope is increasing. There's a little bit of a struggle with the words between increasing graph and an increasing slope. If the slope is increasing, what does that tell us about the graph? I'm not asking you here where the slope is positive or where the function is increasing. I'm asking you about an interval here where the slope is increasing. So anyone out there want to issue, and this was covered on, I think, the activity 14. We had looked at intervals where the slope was increasing and intervals where the slope was decreasing and how that built into the ideas that we covered earlier. So someone out there, and I can see two intervals on this graph where the slope is increasing. Can someone find one of those intervals and tell me why the slope is increasing there, and what the graph looks like to show me that the slope is increasing? From points B to C. Yeah, that's one of them. Excellent. So the slope is, if you consider what the slope is back here, maybe back here the slope is m is a -3. Over here, maybe m is a -1/2. Here, of course, m is 0. Maybe right there, m is equal to 1. So as I read across from left to right, the slope is increasing. And on that little interval where the slope is increasing, that's also concave up. So if I were to put numbers on that one, I would say maybe from 15 to 22 for an interval. And problems like this on today's exam, these are multiple choice questions, so you're not going to have to, it's going to be obvious, from the multiple choice answers, what I'm considering the inflection points and the critical points. So you're not going to have to, do any rounding here. I was quite clear, there's nothing close to except for the correct answers on any of these multiple choice. The second one where it's concave up would be from 0 to A. That's also where the slope is increasing. The slope is decreasing from here, from A to B. Here the slope, say for example, is 5. Here the slope is 0. Here the slope is -1. Here the slope is -3. So as I read along the graph from A to B, the slope starts out fairly big, gets to 0, and then falls down, gets more and more negative as I get closer and closer to B. So here's a place where the slope is increasing, concave up. Here's an interval where the slope is decreasing, concave up. Here, I'm sorry, concave down. Here's an interval where the slope is increasing, concave up. And that little tail at the end is a place where the slope is decreasing again, and it's concave down. So if you have all of that stuff understood, then that several question long multiple choice test questions, they should go pretty well. Oh, by the way, this doesn't go to infinity. This is just the value of the function for the first 25 months, so the first 2 years and a month after, I guess that would be through February 1st, 2012. We really don't have any information about the value of the business after that, so we can't say that this is going to infinity. We just know what the value was for that 25-month period. We can't make any assumptions after that, nor can we make any assumptions before that. That's all the data we have is for that 25 months. Any more questions on anything on problem 3? If so, now's the time to ask. If not, I'll be happy to turn over to whatever other questions you might have. Number 10 on the review. Sure, Drew. I worked this one yesterday, and I'm going to sort of do the same thing today. I find often it's easier on a problem that's has a number of steps. If I can work it through with a solid situation that I make up, then when it comes time to do the second case where I'm not sure what a value of some variable is going to be, I can realize that I need the same steps. So we have to, in both cases, we have to manufacture 720 of these specialty items. 7,200 of those specialty items. The cost is $765 for machinery setup and $340 to store. Okay, so I'm going to start on part A. On part A, that's where I am manufacturing these at 800 items per run. And then I'm going to go sort of back and forth here with part C. In part C, I have X items per run. That's a really important statement right there. I now know what X is. So when I work through the whole problem, if I'm trying to minimize the cost, the X value that I get isn't going to be the minimum cost. It's going to tell me how many items I should do per production run to make that cost function be as small as possible. So in part A, I wanted to figure out what the annual setup cost were going to be. Well, I need this many items, and if I do those in lot sizes of 800 apiece, the number of runs that it's going to take, the number of production runs per year, that many items divided by that many per production run, it's going to take 9 runs. And therefore the setup cost starting to run a little low on brown ink there. The setup cost is going to be the number of runs, 9 runs, multiplied by the cost per run, which is 765. And if someone would take the time and tell me what that number is, I'd appreciate it. I didn't write it down from yesterday. So I'm going to work the same. Now I'm going to do the same thing over here where I have X items per run. Well, what did I need? I needed 2 steps. First, I had to figure out how many runs it was going to take, and then I was going to multiply that by the $765 per run. So if I do 800 items, the way I got the number of runs was I took the total number needed divided by the number of items per run. So this should be 7,200 over X. That's the number of runs I'm going to need in a particular year if I'm going to minimize the cost. So now I have 2 distinct items that I know. X is the number of items per year. 7,200 over X is the number of runs that it's going to take per year. Now finally we're able to get the setup cost. The setup cost is, let's see, the number of runs, this many production runs, multiplied by $765 per run. And while we're at that, let's put this in one nice expression. So what did we get? 68.85, thank you. So this was 68.85. And if I multiply 7,200 times 765 over X, that's going to tell me then the setup cost. If I do produce X items per production run, someone tell me what that numerator should be if I multiply those 2 fractions together. Yeah, 5508. Okay. So my setup cost here are going to be 5508,000 over X. I'm going to keep that in my back pocket. It's going to have to bring it back later. Right, now let's consider the storage cost. Find the annual storage if 800 items are produced per production run. So here's what my items in storage are going to look like for this year. I'm starting with 800. Let's see, I had to do 9 runs, so a ninth of the year later, I'm down to 0, back to 800, down to 0, back to 800, down to 0, back to 800, down to 0, and that continues 9 times during the course of the year. So I'm not going to have all 800 items in storage for a very long period of time. Sometimes I'll have 800, sometimes I'll have 0. On average, I'm going to have 400 items in storage. So I'm not going to pay to store 800 items for a full year when that's not what the situation is. Likewise here, if I have X items per production run, the graph would look the same. I'd have X items per run, sell them to 0, sell them to 0, sell them to 0, sell them to 0. On average, I will have X over 2 items in storage. And the number of items in storage on average, that's what I'm going to help me figure out the storage cost. It's $3.40 per year to store each item. So if I have 400 items on average, and I multiply that by $3.40 per item, I think I can do this one in my head. 16, 31, 12, 13. Let's see, that would be this, I believe. So $1,360. Someone with a calculator, make sure that I got that right. It'd be a little easier in this case if I have this many items in storage. Multiply that by $3.40 per item, 1.7x. And that should be the storage cost. Yeah, 1360 is good. Okay, thank you. Now, if you notice, the storage cost here was significantly less than the setup cost. So my thinking is I am going to do more items per production run. That'll help lower this production run setup cost quite a bit, while not bumping up the storage cost quite that much. So my guess is I'm probably going to, when I minimize this cost function, it's probably going to be a situation where I'm producing more than that each month. So I have parts A, B, C, and D done sort of out of order. A, B, A, C work together, B, D work together. So the only variables that I have in this cost function are setup cost, storage cost. So now I'm going to go to part E. On part E, we have the combined setup and storage, 5,508,000 over X plus 1.7X. Now, if you want to check your work and make sure you got this right, go back, plug in 800 for X, see if when you plug in 800 you get this, see if when you plug in 800 you get that. That's why I reserved those two numbers, just to make sure I wouldn't screw this up. If those two reconstitute themselves, I'm feeling really good about this. Keep that in my back pocket because I want to know what those things all stand for. I'm going to minimize this function. I'm just going to go through. Someone might have to do a little bit of algebra for me, a little bit of calculation for a second. I'm going to take a look at C prime, realizing, of course, that I could rewrite this as 5508000x to the minus 1. When I take the derivative of that, I bring that power down. Keep the x, reduce the power by 1. So I could rewrite this C prime of x as negative 5,508,000 over x squared. It's always easier for me to do algebra with positive exponents, plus 1.7. So there's the derivative. One more time, my analysis of every algebra equation to solve is how many x's exist. In this case, there's only a single x, so I should be able to get that on one side of the equation and then move everything else to the other. Remember, as always, we want to set this equal to 0. We're interested in the place on the graph where the slope is 0. So let's see if we can find that. If I set that equal to 0 and solve, I'm going to move this to the other side of the equation by addition. 5,508,000 over x squared will equal 1.7. I'm next going to multiply both sides by x squared so that I don't have fractions any longer. Now I'm going to divide both sides by, whoops, put your square, there we go. I'm going to divide both sides by the 1.7. And if I recall, this comes out to be 2560000. That's x squared. I think I worked this problem Monday and yesterday, but I'm not sure. I know I worked it yesterday. Did that number come out right? When you divide the 5,508,000 by 1.7, is that truly 2560000? Oh, okay. Thank you, Aaron. I was thinking maybe of a different problem. Maybe one of that I covered on Monday. 240. Okay. Oh man, the other one I knew the square root of. This one I don't know the square root of. Oh, so what is the square root of that? Aaron and Drew were on the same wavelength there. 18. Okay. So 1,800. Remember again, X is a number of items per production run. So on a problem like this one, you work it all the way through, I could ask you, okay, how many items per production run will minimize the variable cost function? How many production runs would you need? What would the setup cost be? What would the variable cost be? Before I answer those questions, I'm going to make just double sure that I have a minimum here. So I'm going to take the second derivative. C prime was negative 5,508,000 x to the minus 2 plus 1.7. C double prime, if I bring the power down, reduce the power by 1, I get 11, 1, 6, 016,000, x to the minus 3. Now what I want to do in the second derivative test is I want to plug in my critical point, which is 1,800. And I'm not necessarily going to find out the exact value of that. The critical thing on this one is to tell whether or not that second derivative is positive or negative. Positive divided by a positive is positive. The graph, therefore, is concave up at that critical point, and since the graph is concave up, I have indeed found the minimum value for that cost function. Okay, now we can go back and wrap everything up. X came out to be 18,000. That's the number of items that we're going to do per production run. Here's the number, even 3, the way it looked. No, and even 4. Yeah. 4 runs per year. No. 18 times 3, 24. Okay. 9 divides into both of those. 8, 2, that's 4. 4 runs per year. So it looks like we should do 4 runs per year. And now let's go back and figure out what these two costs are. If I plug in 1,800 here and I plug in 1,800 here, that'll give me both the setup and the storage cost. And what do each of those, I know they came out to be the same number, what do each of those come out to be? And if you add those two together, $6,120, that would be the combined cost if we do 1,800 at a time. It's quite a bit cheaper than the $6,885 plus the $1,360 I had in the beginning. In the beginning, that combined cost was over $8,000. So that's problem 10. Done slowly and carefully. You might notice on this problem there are just 3 numbers to start with. The $3.4 per year, 3.4 divided by 2 times x, that's a 1.7x. And the other 2 numbers are 7,200 and the 765. That number up there is those other 2 numbers multiplied together. So there's the half of the 3.4, and that's the other 2 numbers that are multiplied together, the 7,200 multiplied by the 795. So when you, or 765. So when you get used to seeing this problem, you should be able to get to, with enough experience, be able to get to this entire cost function in less than a minute. Okay. If you really understand how all this works, less than 1 minute and you have that combined cost function done. So if you want to go back and look at problems like this, you can go back into your grade book on MyLab Math. I think there were at least 3, maybe 4 of this type of problem on the assignment. I think it was optimization part 2. I won't change the grade at all, but you can go back and practice these, practice setting them up, see how quickly you can get from the beginning to the end. Next question. Question 11. All right. Oh, yeah, you had it earlier, didn't you, Matthew? Sorry about that. You're fabricating a rectangle out of stock that measures 15 by 12. On the test today, I didn't include a drawing. You can just assume that we're doing this problem the same way we've been doing it. So we're going to cut out those corners, and I'm going to fold. Maybe I'll make those lines a different color. those red lines. If we do, get a box that shapes something like that. Okay. So again, I'm going to do two problems simultaneously. I'm going to do problems A and B. Part A, well, the size of corner that we're cutting out of each of those is 4 inches. So if this is a 4-inch corner cut out of here, and that's a 4-inch corner cut out of there, remember we started with 12 here, so we cut a 4 there, a 4 there. That means there's only 4 left over for that dimension of the box once we fold up the corners. Again, remember that this was 15 across in the beginning. If we lose 4 here and we lose 4 there, there's 8 total lost. That means there's 7 for this dimension. And if this is indeed a 4-inch corner that we've cut out, when we fold that flap up, the height is going to be 4. Okay. Same sort of idea for part. Let me put my letters over here, huh? So there we have part A. Now let's consider part B. On part B, these are no longer 4-inch corners cut out. These are now X-inch corners cut out. So when I go to draw my completed box, I'm going to have to make my decisions based on a value of X, not a value of X that I don't know. Well, let's see, if this started out 12 and I lose an X there and I lose an X there, this must then be 12 minus 2 of those X's. That will be the dimension of, I guess, the width of the box, maybe? And you might want to check your work, plug in X equals 4. Did that return the 4 that we had there? Sure. 12 minus 8 is 4. We started with 15 across here. We lose an X on this side and X on that side. That must be 15 minus 2X. Again, I'm going to check my measurements. If X was 4, then this becomes 16 or 15 minus 8, which leaves us 7. So I like that. An X-inch tab is going to be folded out. So one more time, I take a deep breath. At this point, I make sure that these two align beautifully. I'll plug in X equal 4. Does that return that, that, and that? And it does, I can tell by a quick investigation. Okay, now what I'm trying to do is maximize the volume. And I also need to find the working domain of this one. Well, it doesn't make any sense for X to be less than 0. Otherwise, if I do, I'm not holding any volume at all, and it doesn't, even X equals 0 doesn't make any sense. But there also is a limit. I can't cut a corner out here that's 20 inches square because I don't have 20 inches of cardstock. So I'm going to focus in on the narrower of the two sides. This is 12. I can only cut out corners here that take up less than half of that. So this X has to be less than 6. I, for example, can't cut out a 7-inch corner from here because there's not 7 inches left down there. So there's the working domain. Any number that I plug in here, any number between 0 and 6, will result in me having some sort of a volume. The volume function, and I'm not going to graph it in any detail at all, but I know if I plug in 0 here that there won't be any volume, and if I plug in 6, there also won't be any volume. So the graph is going to look something like that. It won't be a parabola because the function is a little more complicated than that. I know at 0, it's equal to 0, and at 6, there will be, if I cut out a 6-inch corner, there will also be absolutely no volume. So let's take a look at part B. Take a look at that box and see if we can make the volume be as big as possible. So the total volume here, volume is going to equal x times 12 minus 2x times 15 minus 2x. I want to maximize that, which means I want to find a point somewhere between 0 and 6 that has the maximum value. I want to take the derivative and set it equal to 0 to find that critical point. Before I do that, I'm going to multiply things out. See, those two first, 12 times 15 is 180 minus 24x minus 30x plus 4x squared. So I did this yesterday, and this seems to ring a bell. Let me know if you got something somewhat differently as I go through this, okay? All right. So V is also then equal to, I'm going to combine those two and distribute in one step, 180x minus 54x squared plus 4x cubed. So I combined those two, and then I took time to distribute that x through there as well. I did that in one step. Does that look right? I'm going to assume it is. You can tell me via chat whether it is or isn't in just a second. I want to take v prime and set it equal to 0. V prime is 180 minus 108x plus 12x squared. And now I'm trying to set this equal to 0 and solve. And I realized at this point that this is a quadratic equation. One of the reasons I ran you through all that algebra in the beginning was that you could recognize an equation like this and know what to do. So it's a quadratic equation. You could try to factor it. You would be, I think, unable to. Well, maybe you could if you're a really good factor. I do notice that there's a 12 that you could pull out of each of those. You'd feel free to do that. Otherwise, you could start listing these going through the quadratic formula. There's A, there's B, there's C. Quadratic formula, therefore, this will be equal to 0 when x is equal to 108, either plus or minus the square root of 108 squared minus 4 times, for AC times 12 times 180. Divide all that by 2 times A by 24. So negative B plus or minus the square root of B squared. I left that negative out. It's not going to matter. Minus 4AC all over 2A. So I did this one yesterday, and I got two results. And if I'm not mistaken, I'm not going to say anything. Someone tell me what those two results were. I know one of them was in between 0 and 6, and the other one wasn't. So does anyone recall? Or if you want to work this through in your calculator right now, that's fine as well. Well, while you're working on this, I should mention, I guess, once you get used to start setting these up, should be able to get that in short order, right? It's always the same pattern. So if the sides were 18 by 20, this would be 20 and 18, right? Right. So there's just two numbers that appear on this problem, and once you see, if you understand how this works, setting up the volume function should be pretty easy. All right, 6.79 and 2.21. Yeah, those sort of ring a bell from yesterday, so I'm going to go with that. So 2.21. I'm not going to consider the 6.79 because that's out of the domain of the function. Now let's see if we can calculate what the maximum volume is going to be. Let's see, that first one, when I pulled up a 4-inch corner, it was 4 times 4 times 7. That was 108 cubic inches. On today's test, make sure you use the proper units. All right, so that's what we had back when we folded up corner 4. Let's see if we can beat this by folding up a corner that's 2.21. So I'm going back to my volume function. And I plug in 2.21. The volume is 2.21 multiplied by, if I plug in 2.21 there and 2.21 there, that's 4.42. If I take 12 minus 4.42, that is 7.58, I believe. And this is going to be 3 more. This should be 10.58. And I did that mentally. Let me know if those numbers are not correct. Okay. So now let's see if we can remember what each of these stand for. This would be the height. This would be the dimension across the front here. And this would be then the length. So it gives height, width, and length. And if we multiply all 3 of those together, I can tell already we're going to be quite a bit bigger than 108. There's what, 15 times 10. That's got to be way over 150. No, not way over, but some over. So what number do you get when you multiply that times that times that? $177.23. Thank you. That seems to be within the realm of possibility. That many cubic inches. Jacob seconds the notion, so it looks like it's all in favor, and we'll go on to whatever you have next. So what is the next question, if you have a next question? Again, the setup on these, once you catch on, should go really quickly. Algebra and the calculus is always the same. Using the quadratic formula is going to be beneficial to you. Fill up my glass, I'll be right back. Problem 7 on the review, sure thing. Make a chart to show the intervals where the function is concave up and concave down. Well, the first thing to know, function is concave up or concave down. The first thing to know is that the second derivative will yield that information. So what am I I given on this one? I'm given the original function, I think. Yep. So I'm going to have to get to the second derivative. There's my function g minus 6x squared plus 30x. On today's test, it'll be something similar to this. The derivative is going to come really quickly. I just want to make sure you understand how the chart works. So I found the first derivative, use that to find the second derivative. Now, when the second derivative is positive, the graph is concave up, and when the second derivative is negative, the graph is concave down. When the second derivative is 0, it's neither concave up nor concave down. That's going to be the space that separates, the line that separates those two. So we'll set this equal to 0 and solve. 12x is equal to 30. 10 over 4 looks like 2.5. So if I plug in 2.5 here, I get to 0 for the second derivative. So that's the one and only border point between when the function is concave up and concave down. It's only 0 at x equal to 2.5. So it has to be either positive or negative on either side of that. So here comes the chart. First off, I'm going to keep the the second derivative right up here on top, minus 6. It was minus, oh, I shouldn't have erased it so quick, minus 12x plus 30. There's the second derivative. That comes really important on this chart. So here go the categories, or the labels, I guess, for each of these rows and intervals. Test point. Since I'm considering here where the function is concave up or concave down, I want the value of the second derivative of g. And then I'll wrap that up with the all-encompassing what's the behavior. Intervals, any number before my one and only inflection point, and then any number after that inflection point. Choose a number here. I'm going to choose 0. Choose a number here. I'm going to choose 3. Again, these numbers have to be any number, can be any number in each of those intervals. Plug this in the first derivative. 0 times negative 12 is 0. This one comes out to be 30. If I plug 3 in here, it's negative 36 plus 30. This is negative 6. I'm not so concerned with what that number is, but it's going to tell me about the behavior of the graph. Since that's positive, the graph is concave up. And since it's negative, the graph will be concave down whenever I get beyond 2.5. Problem 7, done. Wow, hour's gone already. Next question. Welcome. number 1, activity 17. Yeah, let me see if I can find that. There it is. Office building that must have 12,000 square feet of space. So I'm going to work part B, I think, then work part C. Part B is the case where I know something, and part C is the case where I'm going to use a variable. On part B, I'll set up the function if the front and the back are 320 feet. All right. So I'm going to create, here's the front, there's the back. If I make this out to be 320, and I know that I need a large number of square feet. You know what? I'm going to go part A just because the numbers are going to be easier. Okay. If that's 300, and I know I need 120,000 square feet, well, I know that the square footage is going to be this side times this side. So let's see, what times 300 is that? Well, that has to be 400. So I get this 400 by taking 1,200 and dividing it by 300. On part C, I'm going to figure out the dimensions pretty much the same way. If this is X and they're 120,000 square feet, then this has to be 120,000 over X. It has to be the number of feet on that side. Now I'm going to find the cost of the shell of the building for both cases. So I now know the dimensions. I have the dimensions set. So let's add the cost of the front plus the cost of the back plus the cost of any side times 2. Since there are 2 sides and they cost the same amount. Okay, the cost of the front is $450 per foot. So that's going to be 450 times 300. The cost of the back is only 200 per linear foot, yep. So that's 200 per foot times, it's 300 feet long. Now the sides, so I'm going to add on to this plus, have 2 of those, same size. Each of those is 400, each of those costs $200 per foot, and each of those is 400 feet long. So on all of the cases, it's the number of dollars per foot times the number of feet, 450 per foot on the front times 300 feet, $200 per foot times 300 feet on the back, $200 per foot times 400 feet on each of the sides. And since there's 2 of them, I'm just going to double that. All right, so add those numbers up. Tell me what you get for the total cost of the shell. I'm going to do the same work over here on the numbers that I don't know. The front is $450 a foot. There are X feet of frontage. The back is $200 a foot. There are again X feet of frontage. For each of the sides, there are $200 per foot, and the number of feet on each of those is 120 over X. So if you want to go back and make sure you have this right, you plug in X equals 300. Yep, that looks right. Yep, that looks right. And sure enough, that should come out to be right as well. So there's my cost function, and I'm going to simplify that cost function as best I can. C of X is 650X plus 1, 2, 3, 4, 5, 6 zeros, 24 million over X. So there's the cost of the shell. Oh, thank you, Carson. 355,000. Even, okay. Okay. Now let's see if we can minimize the cost function. Well, if you look at this one and you look at, I think the very first one we did on today's review where it was the inventory problem, these are set up exactly the same. We have a linear and then we have something that's x to the minus 1. I'm going to keep that 355,000 in my back pocket, see if I can come up with a number that's lower than that as I go through this. So C prime, 650 minus 200 or 24 million over x squared. Remember that this is 24 million x to the minus 1. Bring the power down, reduce the power by 1. It looks like that. We will set this equal to 0 and solve. Move that to the other side to make it positive. Multiply by x squared. There we go. So clear out the fractions just like I did before. Divide by 650. And now a calculator is going to be really handy. What do I get if I take 24 million and divide it by 650? $36,923. Okay. So take the square root then. And what does x turn out to be? $192. Now remember that our x was limited. We could not allow that x to be smaller than 300. And if you look at this function, it's an increasing function right up until you get to 192. It's a decreasing function until we get to 192. Then the costs increase. So the best we're able to do is to make this building be 300 in the front by 400 on the sides, and that will indeed be our minimum cost. We're not allowed to have that x be less than. Right? Any other questions? Oh, wait a minute. Okay, I might have done that part wrong. Let me go back and change these numbers. The sides were going to be 2 of those. They were 120,000 over X, and each of those was 200 a foot. Okay, so yeah, there's a slight error here. It's not going to change the work too much. This one should have been 48. That would have been 48. That would have been 48. That would have been 48. This would have been double that much. So about a 73,846. And the square root of that would have been a little bit less than 300. It would have been 200 and change. Yeah. Sorry about that. Yeah. So I did that one. I did that one slightly wrong with that one number. But regardless, this X that you calculate with a square root there, that still comes out to be less than 300. It's 200 and change. And we're not allowed to build it because it would look dumb. Go over number 8 on the review. Sure, Nicholas. So on the review, I'm going to do 2 pieces sort of simultaneously as well. I'm going to do parts B and C. So the revenue is going to be the number of tickets sold times the price per ticket. In the very beginning, I'm going to keep a nice little chart here so I don't forget what's going on. In the very beginning, we could have sold 1,000 tickets to the event if the price was $15 per ticket. So our ticket revenue would have been $15,000, but we wanted to mess around with the price a little bit. Every time we reduce the price by $1.50, we sell 40 additional tickets. Okay, so let's see and every time we increase by $1.50, we sell 40 fewer. So if you look at part B, no, we'll do part A. I guess part A is done. Huh? Okay. There's the revenue if it's $15 a ticket. On to part B. On part B, we are going to raise the price to $16.50. Price per ticket is $16.50. And if we do that, we're going to lose out on some ticket sales. We're going to lose out on 40 ticket sales. So that would be 960. So with the calculator at the ready, tell me what number you get there. How much revenue would that be? I'm going to guess it's a little bit more because that was a fairly substantial gain in price per ticket and not many tickets on a percentage basis, not many ticket loss sold. So how much revenue would we have if we do jack that price up $1.50 a pop? $15,840. Good. Okay. On to part C. Well, it looks like I'm on my way to getting more money if I raise the price. So now I'm going to form the equation. I started with 1,000. Every time I raise the ticket price, I lose 40 seats, so 40 ticket sales. The original price started at 15, and if I increase that in an increment of $1.50 a shot. So that to me is the easiest way you could come up with this revenue function. It's not the only way, but it's the easiest and the slickest way. So there's the revenue function, R. of x. And what I do at this point is I step back and I make sure that those first two things make sense. If I allow x to equal 0, in other words, I don't change the price at all, I plug 0 back in here, notice that that restores the 1,000 and the 15,000 in revenue. In this case, it would have been x would have been 1. I would have done one of those $1.50 price adjustments. $16.50. If you plug a 1 in there, plug a 1 in there, it's $9.60. So the question is, what should x be? How many of those $1.50 adjustments should I make in order to maximize the revenue? Well, there's my revenue function. So let's do some calculus and algebra and make this a fairly easy one to complete. Distributing through 15,000, that number always pops right back up. Doing the outside, that's 1500x. Doing the inside, that's minus 900, I think it is, minus 900x. And then doing the last, maybe that isn't right. No, that's 600. Never mind. Did that same mistake yesterday. And then the ends are going to be 40 times 1.5 is minus 60x squared. Ooh, almost ran out of room there. So there's my revenue function. 15 grand from the start of the problem, plus 900x minus 60x squared. Technique on finding the max is, as always, take the first derivative, set it equal to 0. Now let's set that equal to 0 and solve. If I set that equal to 0 and solve, I'm going to erase this just for right now. Have it down there anyway. So if I solve that equation, I end up with x is 900 over 120, which is 90 over 12. Let's see, 3 divides into both of those. 30 over 4, which is 7.5. So it looks like I should make 7.5 of those price adjustments. So let's put all those numbers back in there and figure out what this is going to end up being. So we have 1,000 minus 40 times 7.5. That will be the number of tickets that we sell to maximize the price. And then the price that we should charge, and this is probably the most important thing if you're going to consult someone on this one, $15 plus I'm going to do 7.5 of those $1.50 increases. So plug in the calculator, someone let me know how many tickets we're going to sell, and then let me know what that price per ticket should be. I believe this one comes out to be $11.25. Okay. And 40 times 3/4, that's 30, that should be 300. If I'm not mistaken, this one comes out to be 700. If I calculate those two by multiplying the revenue together, 0, 0, 35, carry the 3, 14, 17, carry the 1, 7, 8, no carry. Oh man, hope that was right. Anyway, someone check all the work there and let me know. Yep, so we got the 700, good. Was the 1125 right? Oh, I have the decimal in the wrong place. Oh. So yeah, those two go away. So it's 11.1125 times 7. Yeah. Oh, the 20, oh, I was way off, wasn't I? I forgot to add the 15 back in. There we go. And I wondered why that was coming out strange. Yeah, I forgot to, I multiplied the 1.5 times the 7.5, forgot to add the 15 back in. There we go. Now it's way beyond my ability to do mental math. So what is, if we do sell them at $26.25 a piece, what will our total revenue be? So this is probably the most important number in the whole problem. Where should we price our tickets? So 7.5 of those price adjustments. $18,375. Thank you. I feel way better than this because when I set this problem up originally, it was what, 15,000. The next one was 15,800 something. This number better be bigger than it was before. So on the summary, and I ask on this problem, I ask one of the three questions. I either ask what's the maximum revenue, what's the price per ticket, or how many tickets would the promoters expect to sell. So I don't ask you to give me all three of those bits, but I do ask for one of those three bits. Make sure you understand where each of those numbers came from and what it stands for. Okay, so that wraps up problem number 8. Anything else on this one? Maybe stick around 7 more minutes. I want to get back to making triple sure that the exam is ready to roll out and doesn't have any more places where there's any doubt about how a question needs to be answered. Welcome. Plus get a little lunch. So the 215 class, it's going to roll out at 2:15. The 345 class, I'll have the numbers switched around. So don't expect that to be exactly the same. The problem will be switched around a little bit as well. If you have any last minute questions? Oh, calculator issues. I didn't address this one. You can use any calculator that you choose, but do your work honestly. I don't want you putting formulas in calculators, things that you should remember. I'm expecting you to remember. Okay. Good luck on today's test. I hope that I get it up and running okay. The quiz seemed to roll out pretty well once I figured out how to get it going. So good luck. Talk to you. I guess the next time we will meet will be a review session, probably Monday right around noon.